You know that feeling, right? When you're staring at something really complex, maybe a tough problem at work, or some dense article everyone's talking about,
Hmm.
and you just wish, like, there was a shortcut, a way to just get the main points without drowning in all the details.
Absolutely. Information overload is real.
Well, that's exactly why we're here. Welcome to the Deep Dive. Consider us your shortcut to understanding what really
Glad
matters.
I'd be diving in.
Today, we are plunging into some, well, pretty fascinating new research. We've got this paper right here, Learning Adaptive Parallel Reasoning with Language Models.
And it's from researchers at UC Berkeley and UCSF. So, some serious brain power behind it.
Definitely. Now, you might be thinking, okay, AI reasoning.
Mm.
Why should I care? If you love learning, if you want to understand things quickly and deeply, this is actually pretty relevant.
It really is, because this
Okay.
paper explores a fundamentally new way for AI, for language models, to think through complex problems.
And that could lead to, much faster, more effective solutions from AI down the road.
Right. But also, understanding how AI is learning to think better, well, it can actually give you some interesting ways to think about how you tackle complex stuff, too.
Okay, so let's set the stage. Our source today, this paper, it's digging into how we can seriously boost the reasoning skills of language models.
Exactly. It's tackling a key challenge.
Yeah.
Current AI methods often kind of hit a wall when things get really tough.
Right. So let's talk about those current methods first. You often hear about chain of thought reasoning. What's that like?
Think of it like the AI writing out its thought process step by step, like a very long, detailed explanation, which can be good, but
But it gets long, right? Super long outputs.
extremely long.
Yeah.
And that takes time, increases latency. Plus, there's this thing called the context window, which is like the AI's short-term memory.
Ah, okay.
If the reasoning chain gets too long, it basically fills up that memory. It can forget the beginning of its own thought process, exhaust the context window, as the paper puts it.
Okay, so that's one problem. It's like trying to solve a complex math problem, but forgetting the first few steps halfway through.
Precisely. Then you have other approaches, maybe trying lots of things at once, like parallel methods.
Yeah, things like self-consistency, where the AI
Ah,
tries like multiple different reasoning paths independently.
right. But the paper points out a key issue there. Lack of coordination.
Huh?
It's like a brainstorming session where everyone shouts ideas at once, but nobody's really listening or building on each other's points. Lots of redundant effort.
So lots of activity, but maybe not efficient progress.
Exactly. The performance gains are often limited because of that lack of coordination.
And then there are more structured ways, right? Like tree of thought.
Yes, those try to organize the reasoning more deliberately, like exploring branches of a decision tree.
That sounds better. More organized.
It can be, but a potential downside is flexibility. They often rely on pre-designed structures, pre-planned ways of thinking.
Like having a map for a specific maze. What if the maze changes?
Exactly. The AI might struggle to adapt if the problem doesn't quite fit the predefined structure. It limits adaptability.
Okay, so we've got these existing methods. Chain of thought can be too long and run out of memory. Parallel methods can be uncoordinated. And structured methods might be too rigid.
That's a good summary of the challenges.
So this sets the stage perfectly for the focus of our deep dive. Adaptive parallel reasoning, or APR. What is it?
APR is introduced as this new framework, and what's really key is the adaptive part. It allows the language model to dynamically choose between reasoning, step by step, like chain of thought, and reasoning in parallel.
So it can switch modes depending on the problem.
Precisely. It's designed to be smarter about how it uses its computational resources. And importantly, the paper emphasizes that APR actually generalizes or includes those existing methods.
Oh, interesting. So it's not throwing them out, but building on them.
Kind of, yeah. It can use sequential steps when needed, but it can also decide to branch out. The core idea revolves around adaptive, multi-threaded inference.
Multi-threaded,
Yeah.
like computer processors.
That's a really good analogy, actually. Think about how modern CPUs have multiple cores working in parallel. APR uses these operations called spawn and join to manage different threads of reasoning.
Okay, spawn and join. Tell me more about how that works. What are the key innovations here?
The first big one is this parent-child threading mechanism. So a main reasoning process, the parent thread, can identify a point where exploring multiple options might be useful.
Right.
And it uses spawn to create multiple child threads. Each child thread gets a specific subtask or a variation to explore.
So it delegates, like a manager giving tasks to a team.
Exactly like that. And these child threads explore their specific paths in parallel at the same time. Critically, they usually only get a limited amount of context from the parent, just what they need for their subtask.
Okay. That avoids overwhelming their own little context windows.
Precisely. And once a child thread finishes its exploration,
It reports back using join.
you got it. The join operation allows the child threads to return their results, their findings, back to the parent thread.
So the parent then collects all that information from its team and continues, but now it's informed by all those parallel explorations.
Exactly. It's a coordinated parallel effort, which is a big step up from just having independent, uncoordinated threads running wild.
That makes sense. Okay,
Yeah.
that's the mechanism. What's the second big innovation? Something about reinforcement learning.
Yes, end-to-end reinforcement learning. This is really crucial. Unlike those structured methods with predefined rules.
Like the fixed maze map.
Right. APR doesn't rely on that. Instead, the language model is trained using reinforcement learning, basically, a system of rewards and penalties.
So it learns from experience.
It learns from experience, it tries different strategies for using spawn and join, for balancing parallel and sequential steps, and it gets rewarded when it successfully solves the task. The goal is simply to maximize success.
So it's not explicitly programmed how to break down the problem. It figures out the best strategy itself through trial and error, aiming for the right answer.
That's the power of it. It learns an optimal reasoning policy.
Wow, okay. That sounds really powerful. The paper uses an example, right? This countdown task. Let's make this concrete.
Yeah, the countdown task is a great illustration. It's a numbers game. You get, say, 4 starting numbers and a target number.
Okay.
And you have to use basic arithmetic, add, subtract, multiply, divide, using each starting number exactly once to hit that target number. Figure 1 in the paper shows it clearly.
Right, I see. Like a little math puzzle. So how does APR tackle this compared to that purely sequential method they call SOS plus serialized search?
This example really drives home that context window problem. With SOS plus none, the model tries one path, then another, step by step.
Like we discussed, the long chain.
Exactly. And as figure 1 shows, SOS plus generates quite a few steps, but it hits that 4,000 token context limit before it finds the solution in the specific case. It just runs out of short-term memory.
It's lost in its own calculation. But APR?
APR handles it differently. The parent thread starts, maybe tries a step or two, and then decides, okay, let's explore a few different operations in parallel. It uses spawn.
So it sends out those child threads.
Right. One child might try adding 2 numbers, another might try multiplying 2 others. They work simultaneously. And crucially, as we mentioned, they only get the necessary context.
Which stops them from hitting that memory limit so easily.
Exactly. And because they explore in parallel, they can cover more ground, potentially finding a solution faster or finding one at all when the sequential method fails. In the figure, APR finds the solution.
That's a clear difference. So what were the actual results? Did APR perform significantly better overall on this task?
Oh, yeah. The improvements were pretty stark. First, let's talk accuracy within the same context window, that same 4K token memory limit.
Okay.
APR achieved 83.4% accuracy, so MERI-WES plus AMI, the sequential one, only got 60.0%.
Wow, that's a huge difference. Over 23 percentage points better with the same memory constraints.
It really is. It shows APR is just much more effective at searching for a solution within those limits. It's using the space more wisely, you could say.
Okay, so it's better in constrained situations. What about when you give them more computational power? Do they scale differently?
That's the second major, finding APR scales much better. They measured performance against the total number of tokens processed, basically the total amount of computation.
Right.
At around 20,000 total tokens, APR hit 80.1% accuracy, whereas another method, self-consistency, was at 66.6%.
So as you throw more compute power at it, APR pulls further ahead.
Exactly. It suggests that APR is better at leveraging that extra computation, likely through more effective parallelization. It can think broader more effectively.
Thinking broader, not just deeper or longer. That's interesting. And the third benefit was latency, actual speed.
Yes, real-world time. They found APR achieved significantly higher accuracy for roughly the same amount of time spent.
Gotcha.
For instance, at around 5,000 milliseconds, 5 seconds, APR was hitting 75.2% accuracy. The sequential SOS plus method in that same time was only at 57.3%.
So in the same 5 seconds, you're much more likely to get the right answer with APR.
Significantly more likely. Better answers faster.
Okay, APR sounds great. More accurate, scales better, faster for the same accuracy. How do they actually train a model to do this? You mentioned 2 stages.
Right. It starts with supervised initialization. Basically, they train the language model from the ground up using example reasoning traces.
But these aren't just normal reasoning examples.
No, these examples explicitly include the spawn and join operations. They show the model how to structure parallel thinking.
Where do these special examples come from?
They use symbolic solvers, specialized programs to generate them. They have solvers that can generate step-by-step traces, like for SOS+, and crucially, an APR solver that generates traces demonstrating this mix of sequential and parallel steps.
So it learns the basic syntax and structure of parallel reasoning from these demonstrations.
Exactly. And an interesting side note, the APR solver itself is less constrained by the context window when generating these examples because it is parallel. So it can create more complex, successful examples for the model to learn from.
Oh, that makes sense. It can demonstrate more complex successes. Okay, so that's stage one, learning the basics. What's stage two?
Stage 2 is the reinforcement learning fine-tuning we touched on earlier. After the model understands the mechanics from the supervised examples, they use RL to optimize its strategy.
So teaching it when and how much to use spawn and join.
Precisely. Using rewards for successful task completion, the model learns to make smart decisions about parallelization to maximize its chances of getting the right answer efficiently. They use an algorithm called GRPO for this.
Okay, learning the optimal policy through rewards. Got it.
Yeah.
Now, efficiency, you mentioned it's faster, but does all this parallel work mean it's using way more resources overall?
That's a fair question. But the paper argues APR improves efficiency in key ways. One is sequential tokens, the length of the longest dependent chain of thought. Figure 6 shows APR achieves higher accuracy using fewer sequential tokens than SOS plus edity. It avoids those super long, potentially inefficient single threads.
So the critical path, the longest necessary sequence, is shorter, even if the total work is spread out.
Kind of, yeah. It suggests more efficient search structure. And then there's the real-world latency we already discussed.
Right, the speed benefit from actual parallel hardware.
Exactly. Because Spawn allows distributing work across multiple processing units, like on modern GPUs. It translates to real speed gains. They showed this with tests on NVIDIA A6000s that 75% accuracy at 5 seconds for APR versus 57% for SOS plus.
Practical speed-ups, not just theoretical.
Okay.
And how much impact did that second stage, the reinforcement learning, actually have? Was it a minor tweak or a big jump?
Oh, it was significant. Looking at figure 5 in the paper, RL boosted APR's accuracy from 75.5% up to 83.4%. That's a really solid gain just from the fine-tuning stage.
Wow. And did the RL change how the model reasoned?
Yes, interestingly, RL led to an increase in both the total tokens used, overall computation, and even more substantially, the number of child threads spawned.
So the learn strategy involved more parallelization.
It seems so, for this specific countdown task anyway. The model learned that exploring broader, more options in parallel was more effective than just trying to think deeper along a single path.
That's fascinating. The AI discovered the best strategy was more parallel exploration. Did RL help the baseline sequential method too?
It did improve SOS plus RL, yes, but the gain was much smaller than for APR, which again suggests APR is better positioned to actually use the insights gained from RL, especially regarding scaling computation.
They did one more check, right? Limiting the number of child threads.
Yeah, an ablation study. They forced the model to use the same high number of child threads before and after RL fine-tuning.
And what happened?
The accuracy improvement from RL largely disappeared under that constraint.
Meaning?
It suggests the main benefit of RL here wasn't just about making smarter micro-decisions within a fixed computational budget. It was more about learning how to effectively scale up the computation at test time, learning when and how much to parallelize to get the best result.
Learning to use more power effectively, rather than just using the same power slightly better.
That seems to be the key insight from that experiment.
Okay, let's try and wrap this up. We've gone through how APR works, the benefits, the training. What's the core takeaway for you, the learner, listening to this?
I think the main message is that APR is a really promising step towards more capable AI reasoning. By letting models adaptively manage sequential and parallel computation, well, it unlocks potential for faster, more accurate, and more scalable problem solving.
It's like the AI is learning to manage its own thinking process more effectively.
Exactly. Learning to think smarter, not just bigger. And maybe for you, the listener, it sparks ideas about how breaking down your complex challenges into parallel chunks could be helpful.
Absolutely. And those results are pretty striking, getting much higher accuracy with the same memory or in the same amount of time. That feels like a real leap.
Definitely. Those are the aha moments. And that finding from the RL stage that broader search seemed better than deeper search for this task is quite intriguing too. It shows the AI discovering optimal strategies.
Yeah, that idea of the AI figuring out breadth over depth for this puzzle is, oh, it's pretty cool.
And connecting it back to your interests, understanding these shifts gives you a window into AI's future. Imagine AI tackling scientific discovery, complex design problems, data analysis more efficiently. It could accelerate progress everywhere.
It really broadens the horizon. So, thinking ahead, if language models can learn to optimize their own reasoning like this, what else could they learn to optimize? What other cognitive skills might they adapt and improve on their own?
That's a great question. And could these AI techniques inspire us? Could humans benefit from consciously adopting more structured, parallel approaches to our own complex problem solving?
Lots to chew on there. It definitely feels like a space to watch.
Absolutely. If this caught your interest, keep an eye on research in adaptive computation and AI reasoning. It's moving fast, and the ability for AI to learn how to learn or learn how to think, that's a really exciting frontier.